In this video, I have taken up two-port networks. A few of my students requested me to make videos on two-port networks. So here is a problem. As I normally make only problems on network analysis. My videos are only concentrating on the solution to several problems on network analysis. I am not covering much of the theory. The theoretical aspects are to be read and understood. Otherwise, if need be, I give a little bit of a theory that is relevant to do the problems. Otherwise, I presume that the viewers who are seeing this video have fundamental knowledge of what do we mean by two-port network parameters, what are the various parameters, how are they associated. Okay, so having said so, let us try to look at this problem. For the network shown in figure below, we are supposed to find what we call as open circuit impedance parameters, Z parameters. Okay, so a quick recap of what do we mean by Z parameters. We will have a quick look. What do we mean by a port? A port is a pair of terminals would constitute a port, right? So in a two-port network, essentially, we have an arrangement like this. So we could have a black box, which would be a two-port network. So there could be a port here, constituted by a pair of terminals. There is another port here, again constituted by another pair of terminals. This is one pair of terminals, this is another pair of terminals. So this would become a two-port network. Suppose I have another pair of terminals here, it would become a three-port network, and so on. Right? So in a two-port network, so we have a structure like this. This is a black box, but conventionally, we have voltages and currents corresponding to each port. So we have four variables. So if we can take this as the voltage here in this port, and V2 being the voltage at the other port, these are the positive directions of flow of current. The current into the ports are considered to be positive directions of flow of current. So this is a two-port network. All right. So in this two-port network, you have in all four variables, right? Four variables. So the way in which we define these variables, we form different parameters, right? So if we talk about impedance parameters, as is the case in this problem, in impedance parameters, so we have V1 and V2 are to be the dependent variables. They are functions of I1 and I2. So I1 and I2 being the independent variables, if we define V1 and V2 in terms of I1 and I2, we get what we call as impedance parameters, right? So let this background be sufficient, and let's go on to say what is this impedance parameter. We can write that along with the problem, right? So this is what it means. So in impedance parameters, our I1 and I2 are the independent variables. It is the current in the, we call this input port, we call this output port. So input port and output port currents are the independent variables, where the two voltages V1 and V2 are the dependent variables. So with this background, we will go ahead with the problem. All right. So I will clear this information, whatever I have written, right? So we will not require this. It is sufficient if I can have only the expressions. All right. So this is the network given to us. So what are we supposed to find? We're supposed to find the open circuit impedance parameters. So in order to determine the impedance parameters, you need to have the you need to open circuit the ports. So what exactly we mean by that? Let us try to write the impedance parameters here. So this is what we mean by impedance parameters are expressed in this manner, that is V1 equal to Z11 I1 plus Z12 I2. V2 is related to I1 and I2 by Z21 I1 plus Z22 I2. So I1 and I2 being the independent variables, V1 and V2 being the dependent variables. Here Z11, Z12, Z11, Z12, Z21 and Z22 would constitute impedance parameters, right? They're also called open circuit parameters, essentially because in order to determine your Z11, Z12, Z21 and Z22, we need to open circuit the ports, like either you make I2 0 or you make I1 0, right? So let's go ahead with this problem, right? So this network is it's a typical structure, and this structure is what we call as a lattice network. This structure is what we call as a lattice network. Though in the problem he has not written it as a lattice network, you have to identify. It's preferable if you can identify it as a lattice network. Let us try to rewrite this network in such a manner that it is easy for us to understand. All right. So let me name the terminals for our quick understanding. I'll call this terminal A. I'll call this terminal B. Let this terminal be C, and let this terminal be D. Okay, so let us try to rewrite this network so that we can understand it in a better manner. So I will rewrite the network. I have come to point A, terminal A. From A, there are two parts. One is 4 ohm, another is 8 ohm, right? So via 4 ohm you will go up to B, via 8 ohm you will go up to C. So I will write that part, okay? So via A, I will go up to B via a 4 ohm resistor. And from A, via an 8 ohm resistor, I'll go up to point D. Okay, so this is my D, this is my B. Okay, from B, if we can see, from B there is an 8 ohm to D, and then it is going to right, from A we have a 4 ohm resistor. I'll put the values. From A to rather C is, this is where was the error. A to B, A to B is 4 ohm, and A to C is 8 ohm. So I'll use yellow color. A to B it is 4 ohm, and A to C it's 8 ohm. From C to D, and from B to D, we have two resistors again. Okay, and I'll get here. And my C and D like this. I think I'll pick up my color. All right. So what I have is here from B to, this is my D. Okay, from B to D, if we look at B to D, there's an 8 ohm resistor. So I'll put this 8 ohm resistor. And from C to D, we have again 4 ohm resistor. So this is 4 ohm. So between A and D, if we look at between A and D, we have V1, I1. Okay, that is the input port. So this is my V1. This is my I1. Okay, so and between B and C, we have V2. This is V2, positive. Okay, so this way is I2. Right? So I've rewritten this network. That's all. So this appears little easy to understand, right? So how do we go ahead? So if we can look at this equation, if we look at these two equations, for this network, we are supposed to determine Z11, Z12, Z21 and Z22. All right. So what is the relationship? So we know what is Z11. So Z11 is V1 to, I will write that part also. Okay. Two-port network problems are in fact easy. Z11 can be determined by V1 to I1, with I2 being 0. Alright, so when I2 is made 0, this is gone, this is 0. So Z11 is V1 to I1, right? So That's how it is. So what is Z12? Z12, if I want to find out Z12, I have to make I1 0. So that is V1 to I2. This is with I1 0. Alright. And correspondingly, if we want to determine Z21, what you have to do is, it is V2 to I1 with I2 0. So when you make the output port open, in other words, I2 not there is no current in the output port, we get two parameters, Z11 and Z21. And when we make the input port open, we get two other parameters, that is Z12 and Z22. Z22 is V2 to I2 with I1 0. Alright, so this is how we write it. So I'll try to make some space. I'll take it here so that I just not go to the very corner. So this is how we define. So we a quick look. We understand the equations like this to the two-port network via Z11, Z12, Z21 and Z22, and these are the values of the impedance parameters which can be found by either making the output port open or the input port open. So when there is an open circuit, there is no current flow. So obviously either you are making I2 0 or I1 0. So in which case you will determine all the four parameters. Alright. So now let us try to work out these things. See in this, so we are supposed to find out the parameters for this particular network. So the relationship between V1 to I1 with I2 0 will give me Z11. So if I can get the ratio of V1 to I1 with this port I2 being 0, that is you are not connecting anything, there is no load connected here, so that there is a current flow, there is nothing connected there. So this is open itself. So if I can determine the ratio of V1 to I1, I'll get the Z11, that impedance parameter. So it is a simple structure. So if we can see V1 to I1, it is nothing but the impedance offered by this network. If we can see, it is 8 and 4 in series, 8, 4 and 8 in series. So 12 ohm and 12 ohm in parallel would make the impedance to be half of 12, half of 12, that is 6 ohms. So I can work it out manually, right? These problems could be a problem for objective examination, objective questions, okay, because one can mentally work it out, okay. So what I mean is, if I can determine V1 to I1 as it is for this network, okay, or this network can be reduced as, what I mean is, it is just like this. It is like okay, a network of this nature now. Okay, this is 8 plus 4, which is 12. This is also 8 plus 4, which is 12. So this is my terminal A, this is my terminal D, and this is where I have my V1, and this is where I have my I1. Okay, because there is nothing connected between these 2 points, so the current that enters here will come via this, and the current that enters here will come via this and this, right? So this 12 and this 12, they are in parallel. So as far as this network is concerned, it is going to be 12 parallel 12. That is, when two equal impedances or resistances are in parallel, the resultant is half of the one of the values, right? Half of 12, right? So what I mean is, my Z11 now is equal to V1 to I1, which is nothing but the total impedance. This is 12 parallel 12. 12 parallel 12. This is equal to 6 ohms. Alright. So Z11 equal to 6 ohms. So we have determined one value. Alright. Okay. So we've determined one value. I suppose that is clear enough, right? So now, what is V2 to the other parameter we have to determine? How do we do? Okay, so with the output port 0, that means I2 being 0, we can even determine Z21. What is Z21? Z21 is V2 to I1, right? So we have to determine what is V2 and what is I1. If I can take the ratio, I'll get Z21. Okay, now what is V2? V2 is the potential difference that appears across the two terminals, right? Here, what is the potential difference that appears? Now, if we look at this circuit, if we go back to this circuit, the current flow will be from A to C here, from A to B here. Okay, so for our understanding, I'll put the polarity. So this is the way there is the potential difference that gets created, this end being positive, this end being negative. All right, so this is how the potential difference gets created, right? So okay, so if we can find out the potential difference between if we have to find out the potential difference between these 2 points, that is V2, we have to go from positive from here in this direction and come back to this point, right? That way it will give the potential difference. That means from B to A, whatever is the drop across B to A, the drop across A to C will give me the potential difference V2. How do we do that? Okay, so you can simply do by potential division. Okay, the potential division. So what I mean is V2, I'll write down V2. If I can determine V2, it is the voltage drop across B and A plus the potential difference between A and C. So that way we find out the potential difference between B and C. This is your V2 is nothing but the potential difference between B and C. Alright. So having said so, what is the potential difference between B and A? B and A. So how much potential gets dropped across this? So if we can see AB and BD, they are in series as far as this pair of terminals 1 and 1 dash is concerned. This is my terminal 1 and 1 dash. Okay, so they are in series. So we can apply potential division rule and find out what is the potential difference across each resistor. Here, the potential difference across 4 ohm, if I have to find out, that is equal to BA, right? So it is V1. I'm going from negative to positive, gain in potential. So I will take minus V1 into 4 divided by 12. Okay, so that is the potential difference across B and A. Let me tell you again. So the potential difference across this resistor would be equal to, this is the voltage V1 appearing across AB and BD, right? So it will divide between 4 ohm and 8 ohm, right? So V1 will divide between 4 ohm and 8 ohm. So the voltage division rule says, if I have to find out the potential difference across 4 ohm, it is the total voltage that is appearing across the series combination V1 times this resistance 4 divided by sum of the two. Okay, so what I mean is, here the potential difference, I will use a different color. This is a very fundamental thing. VAB is 4 into V1 divided by the sum of the two, that is 12. Okay, similarly between B and D, it is here the potential difference between VB and D, if I have to find out, I'm not interested in it right now, it is 8 into V1 divided by 12. That's how you do. Okay, these are the potential differences. Similarly, across A and C, what is it? A and C and D, their AC and CD, they are in series as far as V1 is concerned. So similarly, here between VA and C, it is, I am not getting enough space. I'll try to, where do I write? maybe I'll try to write here. VAC equal to 8 into V1 divided by 12. That's how I do. Okay, so I have found out, I'll go back to the expression. This expression of mine, I'll go back to, this is what it is. Okay, as far as VBA is concerned, now VAC is plus V1 into 8 divided by 12. I suppose this is clear enough. Okay, so I can take as V1 by 12 and this is 4. Okay, so 8 minus 4 is 4. So this is V1 by 3. Okay, so V2, what I have found V2 to be equal to V1 by 3. Okay, this is one relationship I have, equation 1. Okay, now what is I1? What is the magnitude of current I1? Why am I finding it out? Because I am interested in, I found out V2, I will find out I1, then correspondingly I will be able to find out Z12 or rather Z21, right? So what is I1 equal to? So in this network, in the second network, in this network, I can find out what is I1 equal to from my, this is my figure 2. I'll call this figure 2. Okay, from figure 2, from circuit 2, from figure 2, what I get as V1, rather what I get I1 to be equal to, I'll get I1 as equal to V1 divided by 6, right? So the voltage, the current I1 equal to the total voltage divided by the equivalent resistance. Equivalent resistance of 12 and 12 is 6, right? This is my equation 2. Okay, I will divide 1 by 2. I divide 1 divided by 2. Equation 1 by 2. What is it we get? If I do 1 divided by 2, I'll get what is called as Z21. Z21 is V2 divided by I1, which is equal to V1 by 3 divided by V1 by 6. This is equal to 2 ohms. Alright, so Z21, now I'm able to determine Z21 to 2 ohms. Okay? Alright. Now what about the other two? So we are able to find out two things, Z11 and Z21. We have to determine Z22 and Z12. This pair. This pair we need to determine. So in order to determine this pair, so my input port has to be 0. That means I1 is made 0. So we have V2 and we have I2, but I1 is 0. How do we do that? It is the same thing. The network becomes the same thing because it's a symmetrical network. If you can see, there is symmetry. So if you can look at, this is the port wherein we are giving the supply. So you will have the I2 current being distributed between 4 and 8. They will come back here and they'll come back to the negative terminal of V2, right? So it's again, there are two branches, 4 and 8 and 4 and 8, right? So it is like this only. So instead of A and D, you will have here B and C. That's all. That's all. So if you can see, if you can identify this as a symmetrical network, then by symmetry, we can simply conclude by symmetry, we get Z22 equal to Z11, which is equal to 6 ohms, Z12 equal to Z21 equal to 2 ohms. It is that simple. All right. So that would end the problem. Okay, the symmetrical relationship can be seen, I suppose. So if you want, I will give you another, what do you call this part. I will copy I'll paste it here. Now what I mean is this won't be A. Now this is my B. This is my C. Okay, and now this would be my I2. This would be my V2. That's all. I suppose you are able to understand. Okay, it is the same thing. So from this network, from this network, so we will determine the other two parameters, that is my Z12 and Z22. These two things can be determined. Alright? So in order to determine Z12 and Z22, we need to make I1 0, right? So I1 is 0. So where is I1? Here in this network we have submerged the input port. So I1 is not being visible at all. Right? So I1 is made 0, but there is I2, there is V2. So I2 and V2 would be used to find out the various other relationships. Alright, so that completes the problem. So problems of this nature can be given as a, what you say, a quiz kind of a question or an MCQ. Okay, so the explanation has become little elaborate, otherwise the problem is very, very simple. If you can reconstruct the network in this manner, so you will be able to find out the Z parameters. So they are also called open circuit parameters. Z parameters are also called open circuit parameters because in order to determine these parameters, you need to either make I2 0, which means you are making the output port 0, or you have to make I1 0, which is nothing but the input port being kept open. So they're called impedance parameters or Z parameters. Okay, so I'll try to take up problems on two-port networks in my further videos. I'll try to cover as many as possible. Right? Thank you for your viewership. If you can post any comments, that will be good for me. Okay, let's catch up in the next video. Thanks for watching.